Have you ever wondered how we came to understand science the way we do today? It feels natural to rely on experiments, observations, and evidence to understand the world. But this wasn't always the case. In fact, for most of human history, people explained the mysteries of nature through myths, legends, and imagination. So, how did we go from stories about gods and monsters to precise methods we use today? It all began when humanity started questioning the world in a more systematic way. This was the birth of what we now call the scientific method, a way of exploring reality that depends on evidence, logical reasoning, and repeatable experiments. But don't be fooled, this didn't happen overnight. It was a process that unfolded over centuries, shaped by brilliant minds of philosophers, scientists, and curious thinkers. Let's travel back in time all the way to ancient Greece. Around 400 BC, philosophers like Plato and Aristotle began developing ideas about how the world worked. Their approach were revolutionary for the time. Plato, for example, believed in a world of perfect forms, the famous world of ideas, an invisible realm of pure ideas that we could only understand through thought and reflection. He was what we might call a theorist, someone who valued abstract thinking above all else. Aristotle, on the other hand, had a more practical approach. He believed that the best way to understand nature was by observing it. For Aristotle, the knowledge of truth comes from experience. He studied plants, animals, and even the stars, recording his observations in detail. While Plato looked inward for answers, Aristotle looked outward. This was the beginning of theoretical and experimental science. And then we run into a man whose contributions were nothing short of revolutionary. The father of modern science, Galileo Galilei. He challenged long held beliefs, like the idea that the Earth was the center of the universe. Through careful observation and the use of telescopes, he showed that the planets, including Earth, revolved around the sun. But Galileo didn't stop there. He believed that science needed more than just observation, it also needed mathematics. For him, the universe was like a giant book written in the language of numbers. For Galileo, science only really works when we combine logical reasoning and practical experience. He believed that to truly understand the world, it's not enough to just think about it. You have to observe, test, and experiment. And that's where hypotheses come in. But what exactly is an hypothesis? Well, a hypothesis is simply an initial idea, a possible explanation for something we're trying to understand. For example, imagine you're looking at a tree and you think, do leaves fall faster when it rains? That's your hypothesis. It's an assumption, something that hasn't been proven yet, but that you can test to find out if it's true. One of Galileo's most famous experiments involved dropping objects from the Leaning Tower of Pisa. At the time, people believed that heavier objects fall faster than lighter ones, an idea proposed by Aristotle. Galileo decided to test this hypothesis. According to legend, he dropped two objects of different weights from the tower and found that they hit the ground at the same time. This simple but groundbreaking experiment showed that weight doesn't affect the speed of a falling object, a concept that paved the way for Newton's laws of motion. More than that, he created a mathematical model to explain the motion of falling objects through his famous method using inclined ramps. And that's exactly how Galileo did science. He showed that to truly understand how the world works, we need to pause, observe, create hypotheses, test, measure, and repeat over and over again. But he also made one thing very clear. A theory is only valid if it can be confirmed by experiments. And that's exactly what makes the scientific method so powerful. It doesn't depend on opinions or beliefs, but on evidence. It's a process of discovery that starts with curiosity, moves through logical reasoning and ends with practical experiments. And guess what? It's still the foundation of science today. So the next time you think about Galileo, remember, he wasn't just a guy who looked up and saw Jupiter's moons. He was the guy who taught the world to ask questions and systematically search for answers. He showed that science isn't a journey of certainties, it's a journey of discovery. But the story doesn't end there. After Galileo, the scientific method continued to evolve. Over time, thinkers like Francis Bacon, René Descartes, and Immanuel Kant would build their work refining the way we approach knowledge. Bacon emphasized the importance of systematic observation and experimentation to exclude biases from the conclusion. He argued that we should base our conclusions on evidence, not assumptions or traditions. Descartes, famous for his phrase, I think, therefore I am, brought mathematics and logic into the picture, laying the groundwork for more structured scientific method. Let's not forget Newton and his monumental contributions. Sir Isaac Newton took the ideas of Galileo and Descartes and combining them into a unified framework. His book, Mathematical Principles of Natural Philosophy, affectionately called the Principia, introduced the world to the laws of motion, calculus, and the universal gravitation. Newton's work didn't just explain how objects move, it also showed that the same laws apply everywhere in the universe, from falling apples to orbiting planets. As science advanced, so did the methods used to study it. By the 18th and 19th centuries, the scientific method had become more formalized. Scientists began conducting experiments with greater precision, using tools like microscopes and thermometers to collect data. The Industrial Revolution brought even more advancements, as new technologies allowed researchers to explore previously uncharted territories, from the microscopic worlds of cells to the vastness of space. The 20th century saw yet another leap forward. Philosophers like Karl Popper and Thomas Kuhn introduced new ways of thinking about science. Popper, for example, argued that scientific theories should be testable and falsifiable. In other words, a good theory is one that can be proven wrong if the evidence does not support it. Kuhn, on the other hand, showed that science doesn't progress in a straight line. Instead, it goes through periods of stability, called paradigms, which are occasionally overturned by revolutionary discoveries. Moving on to nowadays, the scientific method has become more powerful than ever. Advances in technology have given us tools like supercomputers, particle accelerators, and space telescopes, allowing us to explore everything from the tiniest particle to the edges of the universe. We've also developed new methodologies like big data analysis and artificial intelligence, which help us process vast amounts of information and uncover patterns that were once invisible to us. But scientific methodology isn't just about high technology tools and groundbreaking discoveries. At its core, it's a way of thinking, a process of observing, questioning, hypothesizing, testing, and analyzing. It's about being curious and asking, why does this happen? Or what if we try this? It's about challenging assumptions and being willing to change your mind when the evidence tells you wrong. This whole historical journey shows us how scientific methodology has evolved from the time of the classical philosophers in Greece to the present day. But now, the big question is, how are we going to approach scientific methodology in this course? So, we're going to combine the methodology proposed by Galileo and Newton with modern scientific tools. And to get started, let's think of a case where we could actually apply this methodology. In our case study, we're going to define the steps of our scientific method. That means following a structured process, observing an event, formulating a hypothesis, experimenting, and drawing conclusions based on the evidence. Let's break it down with a simple example. Imagine you're walking down the street and suddenly your phone dies. What's your first reaction? If we apply the scientific method here, our first step is observation. The observation is the phone is off. Now comes the second step, hypothesis formulation. We start asking ourselves, why did the phone turn off? Maybe the battery ran out. Or even worse, maybe the phone completely burned out. If that's the case, we would have to come up with even more hypotheses to figure out what happened. So let's move to the third step, experimentation. We plug the phone into a charger and check the battery level. If it's at 0%, then the most plausible hypothesis is that the phone simply ran out of battery. Finally, we analyze the results. After a few minutes of charging, the phone turns back on to life and only shuts off again when the battery runs out. The conclusion is the phone died due to the lack of battery, which was proven through evidence and testing. This simple experiment illustrates how we will work on our case study later in this video. But what are we going to call this case study? We'll call it a project. A project can be anything from creating a project to solving a problem. Unlike continuous activities, a project has start and finish dates. And for everything to run smoothly, we need a well-organized plan. This plan includes defining the scope, what will be delivered at the end, and managing key resources such as time, money, materials, and staff. Everything needs to be carefully thought out for the project to be successful. For example, in a software project, the end result is a working program. In a construction project, the final goal is a completed building. Let's talk about the 5 key stages of a project. Stage 1, initiation. Identify the problem or need and define the main objective. Stage 2, planning. Detail the tasks, estimate time and costs, and organize the schedule. Stage 3, execution, which means carry out the planned activities. Stage 4, monitoring. Track the progress, solve problems, and make adjustments according to the needs. And stage 5, closing. It's time to finish the project, deliver the results, and evaluate the lessons learned. This structure reduces waste and increases the chances of success. Projects are essential tools for innovation, achieving goals, and solving challenges, whether in work, school, or personal life. Now, let's apply this methodology to a real case study. Our case study will be monitoring forest fires using ground sensors and satellites. We'll follow the 4 steps of Galileo and Newton's scientific methodology: observation, hypothesis, testing, and analysis. Step 1, observation. The problem we identified was the increase of wildfires. Fires destroy forests, threaten biodiversity, and increase the carbon emissions, worsening the global warming. Data shows that fires are more frequent during dry seasons or due to human activity. And about this matter, traditional manual monitoring is ineffective, highlighting the need for a faster and more accurate solution. Step 2, hypothesis formulation. Our hypothesis is, if we use ground sensors that measure temperature, humidity, and gas levels, and integrate this data with satellite images, we can quickly detect fires and prevent their spread. This idea is backed by studies showing that changes in these environmental factors are early indicators of wildfires. Satellites would expand the monitoring and accessibility range by remote imagery and data retransmission. Expected outcomes are reduced detection time and increased response efficiency. Step 3, testing. To test our hypothesis, we installed sensors at strategic points in forest reserves. These sensors continuously measured temperature, humidity, and gas levels of CO2 and methane. This data was sent to satellites and relayed to a central monitoring station. When sensors detected critical changes, such as rising temperatures and dropping humidity, the system automatically triggers alerts. Additionally, the satellite's imagery provided heat maps pinpointing high risk areas so firefighting teams could act before fires spread out of control. Step 4, Analysis. The results showed that the system was highly effective. The sensors detected hotspots with 95% accuracy. Response time was reduced by 40%, and in monitored areas, fire damage decreased significantly. Final conclusion is our hypothesis was correct. The sensor and satellite system is an efficient tool for wildfire prevention. The project helped protect biodiversity and reduce carbon emissions. So let's do a quick recap. What did we learn? We started by exploring the history of science and how scientific methodology has evolved over time. We saw how modern technology makes the process more flexible and adaptable. Then, we applied the methodology to both a hypothetical and a real world case, proving that the scientific method is still the foundation of discovery today. And stay tuned because the next videos will talk about space and how satellites play a key role in modern science.